picture to remind you what is the UCB. Let's see if I can find the note here. So this was from last time. And so the idea with UCB is you have some distribution of what an arm is doing, and maybe it has some mean, which I'll draw over here. That's what we've been calling average. Oh no. Okay, one sec. I'm having a little issue on my side here with the chords working as intended. Let's see if we can convince them to work. Okay, it's working. Okay, so what was I saying? I was saying we were working on choosing the best option available to us. And what kind of information do we have? We have the average, which I wrote with AVG. And this really is like the honest average. It's like what we saw first time, our sample number 1 plus sample number 2 plus dot 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 plus sample number n divided by n. And the problem that we're having is that the average that we see, if we have a small sample size, might be far away from the true average, right? So the true average is some other number over here. Maybe I'll draw it in a purple color. So that was what we were calling mu. And the problem is our knowledge of mu is limited by our sample size, so we have some spread. And so we said, when we're choosing things, let's be optimistic. Let's not choose according to what has the best average. Let's choose according to what has the best UCB, U dot C dot B dot, the upper confidence bound. And how do you get the upper confidence bound? The upper confidence bound is equal to the average plus some amount. The average plus some amount. And that amount represents how many standard deviations you want to go up. So plus C times the standard deviation. And C, this is the number of standard deviations we go up. The number of standard deviations we move up. Let's say we add on. Okay. And you might be very familiar if C equals 2 or more accurately 1.96, then you get a 95% confidence interval. And so like if C was equal to 2, then this thing over here would be a 2.5% chance. The tail over here would only be 2.5%. And so we'd be 95% sure that, actually we'd be 97.5% sure that the true mean in pink mu is less than the UCB. So there's sort of a 50% chance that the true mu is either higher or lower than the average we see. But there's a 97.5% chance it is less than the average plus 2 times the standard deviation, because that's how Gaussians work. So this should be kind of review from stats. And now the question that I'm asking you in Mathematize now, related to all this preamble, is what is the effect of changing C? So we can choose in our algorithm what to do. We can either make C higher or lower. And the question is, what effect will that have? And then the question is, what should we do? So what does it do and what should we do? Those are the two questions. Maybe I'll leave 30 more seconds for people to get their final answers in, and then we will take it up. Any other questions or comments about anything else in the course before we continue? Okay, let's see what you guys said. So what does changing C do? And I think there were some multiple choice questions. Okay, so first question, what does changing C do? 10 out of 13 people have said higher values of C do more exploration, and that is absolutely correct. So if you did that, very good. Great job. And indeed, what this is saying, like you can think of this as like how optimistic we are. So if we have, so this was all for one arm. This picture is all one choice. But if we have multiple choices, maybe you could draw them vertically, sort of like this, right? So there's one of them is sort of spread out like this. So there's, that was a terrible picture. Let me try that again. Let's try drawing a Gaussian uppy downy this time in green. So it's something like that, centered around some average. And then we have some other option. Let's make that one blue. Maybe this one is like this. So we're very sure about this one. The blue one we're quite sure about, but it has very small uncertainty. So whatever, we're quite confident that the true average for blue is somewhere over here. The average for green is very spread out. And we're not very sure about it. And what it's saying is if you pick a very high constant C, then you're looking like way up here. So this is like a large value of C is like way up here. So those are large C values are here. And small C values are like here, small C values. And so the bigger you make C, the more optimistic you are, the more you are likely to try an arm that is sort of worse, but has high uncertainty. And the idea is you're going to explore more and then bring that uncertainty down. So maybe over time, the green will shrink, and then we'll know who's better, green or blue, and then we can sort of exploit by picking who's better. So it looks like most people got that one right. Very nice. Now, the million-dollar question, what value of C is best? Which value is the best? All right, and everyone knows the pattern by now, that there is indeed a Goldilocks zone. So high, if you explore too much, that's a problem. If you explore not enough, that's another type of problem. And so I made a little simulator that I was showing you guys last time, and now I have included the thing from before, but it looks like Google erased all my plots. Okay, let's run it again and hope that doesn't take too long. So yeah, remember we were using this to explore all the different types of algorithms. Let me show you the code for what this thing actually does. So it makes a bunch of Gaussian arms. So every arm, the score you're going to get is a random variable, and it's a mean 0, variance 1 random variable, except for the 0th choice is actually secretly mean 1. So the 0th choice is slightly better, and if you play any other arm, you'll have a regret of 1. So here it's calculating the regrets. And then these are all the little algorithms we had. So like this was, if you go random every time, you get a lot of regret. In 1,000 tries, you get like 800 regret, because 19 out of 20 arms have a regret of 1. If you do the greedy, you get this thing, you get a regret of like 200. And then we had these other algorithms, like exploring, then exploiting. And we were optimizing last time. We said the optimal amount is this t to the 2/3, and then you get the lowest amount of regret. You balance exploring and exploiting. And then we had epsilon greedy. We also did the same thing. And we said the best power was this t to the 1/3, the green line. And then we were doing these UCBs. Okay, so in the UCBs, here are some UCBs with different constant C, going from 0.5 to 4, and they have different behaviors. So if you make C too big, let's say C equals 4, it turns out it's too big, then you're spending too much time exploring. So you're doing all this exploring, all the exploring is costing you, and you're doing too much. On the other hand, if C equals 0.5, then you're not doing enough exploring. So you kind of explore for a little bit, and then you're getting this constant slope over here is too high, and that's because you are getting stuck in suboptimal arms, you're not exploring enough. And of course, the Goldilocks zone is, for this problem, is somewhere in between. It turns out it's square root of 2 for this problem. And so that's the best one, 1.414. There is a theorem that says, in general, what you should do is related to the log of capital T. So if you look up this stuff, the optimal C is proportional to the log of capital C. The optimal C is proportional, or related to, let me say related, because it might be the square root now that I'm thinking about it. Let's say related to. Related to the log of capital T. And so it's, the longer you play, the more you want to explore. So if you're going to play, like, you're going to be here for 100 years, then you're going to spend a lot of time exploring up front. And if you're going to play a short round, then you're going to explore less. And so you got to balance and figure out what to do. That's the UCB algorithm. And I'll have more to say about the UCB algorithm later, and that's because the UCB algorithm is the basis for a very exciting paper that we're going to look at today. This paper is called, let me scroll up to the title, drumroll, Mastering the Game of Go Without Human Knowledge. So if you remember, on the very first class, I showed a nice video of this main author, David Silver, who was explaining why it's so important to learn the game of Go, but without any human knowledge. So this was the first computer program that beat sort of grandmasters at Go. And so it's called AlphaZero, and it learns without any human knowledge. So it learns just by playing itself, and it is based on the UCB algorithm. So it's the UCB, and then it's souped up. So we're going to explain how this works. Let me see if I can find somewhere where it says UCB. Come on, show me a UCB somewhere on this page so I can highlight it. Ah, okay, great. Look at here it is. Each simulation starts from the root state and iteratively selects the move that maximizes an upper confidence bound QSA plus USA. So Q, we're familiar with Q. That is how good you think the current thing is. But we don't just pick according to Q. We pick according to Q plus U. And U is adding on this bound to make the upper confidence bound. Okay, so we're going to explain how this works a little bit later today and tomorrow. Okay, so that's why UCB is great. It's the basis of this thing. But before we do that, just a little more practically, I want to think about how could we use this UCB stuff that we've been learning, how can we use that in our programs for assignment 5 and the final project? And so here is the question for you. So in the multi-armed bandits problem, remember that was our setup, our problem where we figured this stuff out. We were using the combination of the average so far and the n to calculate the UCB. So we're kind of in this situation, you just choose what to do, and then you go based on that, and we found this UCB was really good. So that's adaptive exploration. Exploration, spelled incorrectly. In our setting, so in the setting for your final project today, it's not exactly like that. I mean, there's not always the same situation. You don't have this average so far. You don't have this n. But what you do have is you have the QSA function. And in fact, the way we did QSA is we just said, if I take this action, I know exactly what will happen. So the value of QSA is the value of the state S with the move A played. So when you're doing value of moves, that's what you're calculating. So that we have that for every possible action we could take, and we're using like parameters to parameterize this thing, but we have our estimate so far. And the question is, which algorithms can we use with only this limited knowledge? So these are some of the ones we talked about. There's the explore first, then exploit. You spend some amount of time exploring, and then after you're done exploring, no more exploring, only exploiting. There's the epsilon greedy, there's the UCB, or there's pure greedy. Which of these can you do with this limited setup? Okay, looks like some people have answered already. Let me start a timer for everyone else for 1 minute. Okay, looks like there's 2 people left. If the 2 people answer, then we can stop early on the timer. Okay, I think everyone's in. Okay, let's see what people said. And remember, it could be more than one. Which ones can we do? Which ones can't we do? Okay, 13 out of 13 people. Remember that epsilon greedy was the thing we talked about even before we did all this bandit stuff. That is absolutely one we can do. Pure greedy is also one you can do. So if you were doing pure greedy, you would just calculate all the values, and you would always pick the maximum one. So this is one we talked about. The problem with pure greedy is you can get stuck in some situations. So actually, let me show you very quickly why you don't want to do pure greedy. So of course you can do it, but sometimes it's a bad idea. And let me show you, this is tic-tac-toe. This is my sort of version of your assignment 4 of learning to play tic-tac-toe against the greedy AI. So not the random AI, but learning against the greedy AI. And it's set up to do Monte Carlo just like you guys did in assignment 4, and it has a nice little neural network brain. Actually, I don't even think it has a neural network brain. It just has a sum of features. So very simple. And you can see this guy is losing. First, we start out by losing a lot of games. So we lose the first 10 games. 10 games in a row, we lose a tic-tac-toe. And then we start tying games. And we never really learn to win games. We learn to tie games, but we don't learn to win the games. And the reason is we're doing no exploring. I'm going to tell you what this sigma thing is in a minute. But when it's 0, that is the pure greedy algorithm. And what's happening for sure is that the artificial intelligence, the system, thinks that the winning move has negative value, and it has discovered some tying moves. And it's like, these are so great. I get 0 value when I do these. I can get a tie. And then it never tries the move that would lead it to a win. So by always trying moves that are a tie, you never explore the moves that are a win, and that's why it's getting so many ties. Like it has like 50 ties in a row here. This is a nice little plateau of another 50 ties in a row. This last little bit is like 100 ties in a row, except for a couple spikes where we lost. So that's what's going on. So that can happen, and that's quite bad. If you're playing against an AI that is doing the same thing over and over again, like the greedy AI, then you can get stuck and never learn anything. Okay, so you don't want to do that. Okay, so 12 out of 13 people said we can do the explore first, then exploit. And I think you can't. So let me reveal, this was my answer, that 92% of people got wrong. Remember, in the explore first, then exploit, what we do is we play all of the actions sort of equally for a while, and then after that, we play the best possible action. So what would that look like in this setup? I guess you would play fully random for a while. But look, if you're playing fully random for a while, the queue function that you're going to learn is not the queue function according to some strategy. It's the queue function for playing purely random. So the problem is, just like the problem always is in reinforcement learning, the data that you see is a function of the actions that you took. And so if you take explore first, like try everything sort of equally, then you're not going to learn anything. You're going to learn the value function for the play random guy. And that's not what you want. So unfortunately, explore first, then exploit does not work. Another way you could say it is that in the multi-armed bandit problem, we're always in the same state. So if we're always learning about the same state, then we can try everything for a while and see what would happen. But in our reinforcement learning setup, we're always thrown new states. You can't just, if you're just always exploring, you won't actually do anything good. So you'll never actually learn about the state you're in. You'll learn about some other state that you tried 100 iterations ago. And you definitely cannot do UCB. The reason you can't do UCB is you just have Q. You don't have a Q and an N, right? So we were using the N to calculate the confidence bound before, and we don't have an N anymore. And there is no N, because every time you kind of like play a game of tic-tac-toe, it's like a brand new situation you've never seen before. So this like fiction of the multi-armed bandit problem, having the same thing over and over again, is just not true, and we can't do it. So that's quite sad. So was it a big waste of time to learn about this stuff? Well, no, there's ways you can improve it, and that's what we're going to learn now. It's a good place to stop for questions. Any questions or comments about anything?
How does this relate to classic approaches like alpha-beta pruning?
Yes, that's a great question. So I think it's very different. Maybe when I mention the AlphaGo 0, we're going to learn something called Monte Carlo tree search, which doesn't have any reinforcement learning in it. So it's a pure search algorithm. And maybe when I mention that, I can mention alpha-beta pruning, which is another search algorithm, and they'll be side by side, and they will go. But of course, in these search algorithms, what you're doing is you're like searching through all the possibilities, like you're doing computation. In these ones, we're trying to like bake all of the thinking into our neural network, or whatever our parameters are. So we're trying to calculate the Q functions accurately, and then choose based on the Q functions, right? Whereas in a search algorithm, there is no Q function. You just say like, I'm going to try everything and see what's good or bad. So it's kind of a different way of thinking about it. And you'll see that the AlphaGo 0 is like merging those two ideas together. Yeah, great question. Anyone else? Okay, so what we're going to do is we're going to say, okay, was it all a waste of time? You can't literally do UCB, but you can do some kind of adaptive exploration. So I think the big idea to remember of UCB is not literally like what is the actual algorithm, but the big idea is that UCB is adaptive exploration. Adaptive. Right? So the whole shaboodle is that you don't want to try all the possible options because some of the options suck. You want to try the options that have a chance of actually being the best option. So don't be greedy and always pick the best option, but let's try to figure out some way we can pick like the top 3 or something. And the closer the things are, the more we should pick the ones that are good. So choose promising options more. Promising options more. That's the big idea. And if you think about the setup you have for your final project, there is a very simple algorithm you can do to choose promising options more. Or there's actually lots of different ideas you can have. So I wanted to spend like 2 minutes. Let's just brainstorm. What could you do? So how could we, you guys know what you're doing with these neural networks. What could we add to it to try to bake in this idea of doing some adaptive exploration? And that's my next little thing. So it's a little brainstorm. So we can't do UCB. How could we do adaptive exploration? Throw me any idea you have whatsoever, and we'll see what kind of ideas we come up with. Maybe I'll give you like 3 minutes to think and reflect. How could you bake this stuff in to your learning algorithms? Okay, there's like 20 seconds left. I think there's one more person who has to type in their idea. Okay, let's see what everyone said. Reveal. Word cloud. Okay, I don't know. Many moves. Good. The best UCB options. Let's read some of these. Try the third best option. Yes, so you could do something like you could hard code in of the top 3 when we do an epsilon. Pick one of the top 3. That would be super simple, and that would for sure improve it. Especially in games like tic-tac-toe is a great example. Maybe there's like 1 or 2 moves that make sense, but there's like often a lot of moves that are clearly bad, right? And you don't want to, when you're doing epsilon greedy, you're saying I'm going to pick all these moves at random. Like pick the top 3 on the epsilon thing. So that would be fine. One thing that would be tricky is like, should you do top 3? Should you do top 4? So that might affect it. But already that would be a good idea. Okay. Jackknife is another word for bootstrap. So this person is using a stats technique where what you do is you simulate a bunch of times, and then you, based on the uncertainty you get, you estimate the uncertainty for the real thing. So it'd be like I have a bunch of people that I ran from my survey, and instead of getting new people and surveying them to see what my confidence interval is, I just like pick from the box that I have. So that's a good technique. In fact, in some sense, this is pretty close to what the Google guys did for Monte Carlo tree search and AlphaGo Zero. So we will kind of talk about this in a second. This is pretty close to what the AlphaGo Zero is. So it's a good idea, and if you pursue this, you will get something. Yeah, okay, this is a very simple idea. Choose the ones with the high Q values more often. This is essentially what we want to do, right? This is what UCB would do. UCB says don't pick the absolute highest one, but pick the ones that are high, like more, right? They have an advantage. And there's a lot of different ways you could achieve this. Let's see if other people wrote this same thing. Oh yeah, okay, this is another totally good idea. So we'll come back to this one. You could add some other neural network that's like trying to estimate the uncertainty. So you could include in your neural network not just the average, but the average plus the uncertainty. You could make a neural network that outputs the upper confidence bound, right? And then you would choose based on that. How do you train the upper confidence bound? That's a little tricky because it's not just the Bellman equation for the average like we learned in the course later. I'm sure you could do some work and figure this out. And in fact, people call this the at-risk thing. So it's like, imagine you're training a neural network and you don't want it to do the best possible average. You want to make sure it doesn't fall off a cliff, like some like safety critical thing. So then you choose the best possible thing, not based on the average, but the like worst case scenario kind of situation. So it'd be similar to that. So you could do this and you could change the training. That'd be a nice thing to do. All right. Yeah, so this is another person who is, keep track of how many times you visited each state. If you just kind of do this like the straight way, in a large enough game, you'll have visited every state exactly once. Like when you're learning chess, every chess game is a completely new chess game after like the 10th move. But if you do this the right way, you will eventually also discover AlphaGo 0. So you guys are doing great ideas here of kind of stumbling into the Google AI ideas. Yes, good enough options. So this is the same kind of idea as let's choose from the Q values. We'll pick from the large Q values somehow, right? So good enough options. That's very nice. Yes, good enough with a star. Yes, very good. Estimate and yeah. So if you can make a neural network that sort of estimates the standard deviation of your knowledge, or you can keep track of the uncertainty in your parameters or something, you could do that. If you're doing a decaying epsilon, as long as when epsilon happens, you're picking uniformly at random, that's not adaptive exploration. That's still. So the thing we want to eliminate is when we decide to do some exploration, let's not explore the worst case scenario. Let's still focus on the top few moves. Yeah, choose. This is a great idea. That's same as some of these other ones. Choose one with a high value, just not the best one every time. Yeah. So or you could do the third best. Good enough. Okay. I think of some of these I've seen already. Very nice. Okay. So let's go back to this one, which I think is the clearest setting of what I want to get into. Choose actions that have a high Q value more frequently. So this is the idea, right? So in our network outputs Q of SA. So maybe SA1, Q of SA2, Q of SA3, Q of SA4. And again, in your final project, the reason there's no Q value is because it's baked into the value function. So we know the rules. We know what would happen if we played action A1. We would be taken to state S plus A1, plus sort of in quotes, and then we would calculate with a value. So we have all these different things that would happen in the different actions. And instead of always picking the top one, let's pick them with probabilities that are sort of proportional to how large they are. So the larger the Q value, the more we should pick it. So we're going to create probabilities. So we're going to create, and some people use pi for these probabilities. Pi of A1, pi of A2, pi of A3, pi of A4. So we're gonna sort of condense all these Q values down into some probabilities, and we want pi of A is large when Q of SA is large. Okay, and one example that we've been doing the whole time, e.g., you can say pi of A equals 100% if Q of SA is the largest, and 0% otherwise. And that's what we've been doing so far. We're saying, like, if you go greedy, you pick the largest one 100% of the time, and you pick one of the other ones 0% of the time. This is the pure greedy. The epsilon greedy also fits into here. The epsilon greedy is this. It's pi of A. It's 100% minus something like n times epsilon, and it's epsilon otherwise if Q of SA is the highest. Right? So if you're not the highest one, you have an epsilon chance of getting picked. Actually, I guess you have an epsilon over n chance of getting picked, and there's no n usually the way we do it. Okay, so it's like this, where n is the number of choices. So the epsilon greedy says, what is your chance of getting picked? Well, if you're not the highest value, then the only way you can get picked is in this like explore situation where you pick them all equally with probability epsilon. If you're the best one, you get chosen unless the epsilon event happens. I guess maybe it's technically like this, plus epsilon over n, because you could still choose the highest one on the epsilon. But you notice none of these depend on the actual values. These are like a hack to make it work without knowing the values. Could we make it so that the probability, the pi of A, is equal to, and it's just like some function of the Q values, like could we type in what Q is here? So it should depend on Q. Like what if we just do Q of SA? What if we just do that? Then it'll be higher for, what is this? Okay. So what if we just say pi of A equals Q of SA, right? Then if Q is big, then we have a high probability. If Q is small, we have a low probability. So it's a nice idea. Unfortunately, this won't work exactly as written. What's wrong with this equation? Just make the probability equal to Q. Yeah, they don't even sum to 1. Q might be negative everywhere, not even positive. They don't sum to 1. So we got to fix two things. Let's make them all positive. If I do e to the Q, then now it's positive. That's pretty good. How do I make it sum to 1? Well, just do like in your program, do 2 lines. In the first line, make them e to the Q, and in the second line, divide it by the sum, which is equivalent to this. So divided by the sum of, let's call them A prime, and it's e to the Q s A prime. So if you do this, this has a special name. This is called the Softmax choice, or the Softmax probabilities. And you can even include one extra thing to dial things up. You include something called an inverse temperature parameter, beta. Beta is the inverse temperature. And by tuning the beta, you can dial up or dial down how often you choose the best one. And so, for example, if beta equals infinity, in quotes, that is greedy, pure greedy. And beta equals 0 is pure random. And so by tuning the value of beta in between 0 and infinity, you can say how much more you're going to do one or the other. This distribution is used a lot anytime in kind of machine learning. You need to have a probability distribution. This is like how they're created. So you always create some quantities, in this case they're the Q values, and then you're like, oh no, it's not a probability distribution because they're not positive and they don't add to 1. Then you just exponentiate them and divide by the sum, and then it's fine. So this is called the softmax trick, and it's used all the time in machine learning. So that's one way to do it. And this will work very nicely. This is a great idea. There's an even simpler way you can do it. Yeah?
What's the reasoning behind exponentiating instead of just like squaring it or something to make it positive?
That's a great question. You want it to be monotone increasing. So you want larger Q values to have larger probabilities. If you square it, it works as long as they're positive. But then for negative values, it's actually doing the opposite of what you want because the square function is decreasing. Yeah, that's a great question. Yeah.
And then is there any connections between like statistical mechanics? That looks like the Boltzmann.
Yes. Okay, so in physics class, like if you go and you measure particles, it turns out the probability of finding the particles in a certain configuration, how does it work? Probability of particles in configuration, what do I call it, configuration C. It turns out that is also like e to the 1 over the temperature times the energy of C. So with a minus sign. And then times the constant divided by the sum overall. So this kind of distribution, people in the 1800s first discovered that it's like true in particles with respect to the energy. So when you're like watching a bunch of hydrogen atoms in a room move around, sometimes they do things that are like lose energy to the outside of the room, but those things are unlikely. And so the energy is what like controls the probability, and the temperature is what mediates the energy into probabilities. So if you're in a really hot hydrogen, it's going to do all sorts of crazy stuff. really cold hydrogen will just like sit there and like be in the lowest energy state and just sit there forever. And people sort of borrowed that and turned it into machine learning. So yes, that's why people call it inverse temperature. They didn't just make up a wonky name for no reason. Yeah, great question. Anyone else?
Is that connection to the Boltzmann machine?
Oh yes, this is a good question. Is it? Yeah. So there's a thing called a Boltzmann machine, and maybe it's called Boltzmann because of this. I don't know. I don't actually know if it's the same Boltzmann. And probably it's the same guy, and then I don't know if it's the same exact reason. But yeah, definitely same. Boltzmann was some famous guy who discovered like thermodynamics like many hundreds of years ago. Yeah. Okay. Great. So this is one thing you can do, and this is totally nice. If you're like good at machine learning, this is like pretty quick because all of these functions are baked in. So if you like look up JAX, you will eventually find a function that does this. So there'll be like some JAX function that's like sample, and then you'll say like JAX.sample according to Softmax. Okay, I can't think of what this is off the top of my head. Should we? Oh yeah, this will be fun. Let's go ask ChatGPT what it is. That'll be fun. Let's see if I can ask ChatGPT. All right, what's the function in the Python package JAX to sample from a softmax distribution given the values of the logits? So the thing that you're doing the exponent of are the logits. Okay, and it says random.categorical, so random is JAX random. So JAX.random.categorical, you got to do the random key stuff that we always do in JAX. So you got to feed it a random key, and then you feed in the logits. For us, the logits will be all those values, and that will sample from the thing. There is no temperature here. Let's ask it, how do we put in a temperature? How do I put in an inverse temperature parameter? And maybe it'll just say you just multiply. That would be one very nice solution. Yeah, okay, there you go. You multiply them by some value beta, and then it works. So it's like, here you go, beta, the inverse temperature parameter. You scale them by multiplying by beta, and then you sample. So that'll give you samples according to this distribution, and that will automatically do what we're talking about, choose the higher values more often. If it's a sort of a tie, it'll choose them sort of equally. And the bigger the higher value is, the more often it gets chosen. Question over here.
So what actually makes it do that? Is it the categorical?
Apparently, this is what, okay, this is true. I should not say that whatever ChatGPT says is true. But ChatGPT is claiming the command is jax.random.categorical. I guess you would confirm by going to jax.random.categorical, which apparently I've been to before, 60 days ago, yes. So there we go. And yeah, like it didn't lie to me. It really is this. Okay. Yes, so it has something. The logits are the unnormalized log probabilities of the thing. So that softmax of logits gives the corresponding probabilities. So yeah, these things are called logits, and it'll do the way it works. It's a really common function in machine learning, so it's not surprising that it's in JAX with some simple name. Yeah.
Also, is this the same logit that shows up? Is this the same logit that shows up in binary regression?
Yeah, logit stands for like log of probability. So these if you sample from these pies, if you take their log, then you're going to get back the q's basically. So the log of the probabilities are proportional to the q's. Yeah. Okay. So that's one way to do it. There's a very super simple, easier way. Going back to our thing. So if you don't want to do this, we want to pick the largest q, but like sort of randomly according to like not always picking the highest one. What's a simpler way to do it? Here's an even simpler way. So that was one way. Here's an even simpler way. Let's not erase the q. But here's an even easier way. What if I just add on a little bit of noise to every single value? Okay? So I'm going to add on, I'm going to say plus, and I'm going to call it noise. I'll call it n for noise. n1 plus n2 plus n3 plus n4. And then I will just pick the largest one. So I'll just do the maximum of Q of SAI plus NI, right? So choose. And then I never need to worry about calculating these probabilities, right? Like I never even calculate the probabilities. The probabilities kind of emerge naturally by which one is the largest. And whoever is the highest value, if the noise is small, will have a big leg up, right? So it's sort of like I'm adding a little fudge factor to all of them. That kind of reflects my knowledge that I'm not perfect. I don't actually know which one is the biggest. Why don't I just like fudge them all by a little bit, and we'll let like luck decide. There's a famous quote by Napoleon where he was like interviewing some guy to be his lieutenant or something, and the guy like didn't make it to the interview because he like, I don't know, like the bridge he was gonna cross like fell over or something. And he's like, well, that guy's out because I don't want unlucky people in my army. So this way, you know, you're adding some luck to the situation, and you're choosing the guy who was the most lucky. Of course, the people who have large Q values have a leg up. And if you make the noise, you can kind of think about the size of the noise as like the size of your uncertainty of the values. If you wanted to, you could say at the beginning, make the noise values very large. Later on, make the noise values small. And it really helps a lot, even with just keeping them constant. So let me show you in tic-tac-toe the results. So that's what this constant sigma value is. Sigma is the size of the noise. So actually what I did is I did sigma times this, so I could control the size. And in this situation, I made sigma equals the size of the noise. And I used a Gaussian distribution. So n was Gaussian. This is a super simple way to do this, is to add this on. Okay, and if you add nothing, right, if the noise is nothing, then you're literally back to greedy, which is over here. So if you make the sigma value 0, this is literally the greedy algorithm, and nothing will work. I guess I can show you the code of how it's learning. This is exactly the project from assignment 4, where we're updating with Monte Carlo. So this is at the end how we're learning. I am doing the gradient. I'm using the optax thing that I showed you guys to keep making it a little simpler and choose the learning rate correctly, but it is a linear function at the end here. And how am I choosing the best move? I guess I have to go to the AI. Let's go to the AI. What is the AI doing? Yeah, here it is. So this is my function, my AI. And so it takes the raw values of the values. So value parameters moves, calculates the value for every possible move. It's already been jax.v mapped, so it can calculate, you give it all the moves, it calculates all the values all at once. Then this line with the jnp.where sets the value of any illegal move to -infinity. Don't accidentally pick a move that's illegal. And then noise is purely random times sigma. So the bigger sigma is, the more noise. Then I say the noisy values, I add on the raw values plus the noise. And then which move do I pick? Whichever is the best of the noisy values. And so what this will do is if there's like a tie, if there's like two moves that are about equally good, then they're both sort of equally likely to be chosen. If there's two moves that are like both pretty close and like one of them is only slightly better than the other one, then that one will be slightly more likely to be chosen. If there's like two good moves and like 8 terrible moves, I'll never choose the 8 terrible moves because like or I almost never will choose the 8 terrible moves. They would have to get a huge boost from the noise, which is very unlikely. So this automatically is like picking the better moves more often, and it helps a lot. You gotta get it right, sort of. So I did some experiments here. I tried it with 0.02, and this was great. So this is learning to beat the greedy AI in tic-tac-toe in 500 simulations. So in the first kind of 50 simulations, it took me 50 rounds of losing tic-tac-toe to sort of get pretty good. And then after that, I got really good at beating it. And I never had to change it. It was 0.02 the whole time. Sort of by the end of the game, probably it doesn't matter at all, because there's like one good move that it's like narrowed in on. And so this like plus 0.02 won't matter much. Already after 0.02, it starts to get worse. So if you go up to 0.05, 5%, remember, like the value function represents how often you win, right? 1 is 100% chance of winning. 0 is like a 0% chance of winning. So this is like, let's fudge things by 2% or 5%. So this is same kind of situation, but you can see I'm not doing as well. So I only got up to 80, whereas this one I got up to 150. Okay, and then here's another one, 0.1. Same kind of thing. You can see the dip is bigger. So maybe I'm doing a lot of like weird things early on. I compared this to epsilon greedy, so this is the same exact thing, but with epsilon greedy. And I was trying a bunch of different things to make it as good as I could, and I could only get up to like 80, doing this like 10%, 0% thing, which I know a lot of people tried some funny things on assignment 4. but this is like a simple way you can make it do this exploration automatically. Okay, so that's adaptive exploration. This thing has a name. It's called this algorithm is called the follow the perturbed leader. Follow the perturbed leader. That's another Napoleon joke for you. Okay. So the reason it's called follow the perturbed leader is because you don't follow the one who's the actual highest. You follow the one who, when you added on the noise to make it noisy, that's the one you follow. And it's really simple. That's the main advantage. And you can kind of have a sense of what does the sigma value mean, right? And so in the context, if you know the Q values represent winning or losing, you know what sigma represents. Like a sigma of 0.1 represents a 10% fudge. A sigma of 0.01 represents a 1% fudge. Okay, and I can show you some simulations as well. So I did this in the Bandit simulator. And at first I did it, and it wasn't working that well. So let's see. Yeah, so first I did it like this. And the FPL, this purple line, is the follow the perturbed leader, and it wasn't very good. So it's like pure greedy is like up there, right? The epsilon schedule is this orange one. That's when you make epsilon, you make it sort of start large and get smaller as you go. The explore and the exploit is that green line that we optimized, and the UCB is the best one, is the red. And I was like, why isn't it working? And I tried a whole bunch of things to get it working. And I think the reason I figured out it's not working very well is because this is the situation where one arm has a mean of 1 and all the other arms have a mean of 0. So sort of like there's one good choice and there's 19 bad choices. And in that situation, follow the perturbed leader, which is like, what does it do that's good? It's like it narrows down. It doesn't say, when it picks randomly, it doesn't pick like a low guy randomly. It sort of should narrow in on the top guys. But there are no top guys here. There's only one. So it didn't work very well. So I tried a different situation, which might be more like tic-tac-toe or something. So in this situation, there's one arm that is good. There's 10 arms that are a tie. So it's like, imagine you're playing tic-tac-toe. There's one winning move. There's 9 moves that will lead you to a tie. And there's 10 moves that will lead you to a loss, right? And so what you really want to do is don't accidentally play these bad moves, right? And in this situation, the follow the perturbed leader does quite well. So the explore then exploit actually does quite badly because it's spending a lot of time exploring these stupid -1s that are bad. The epsilon greedy, it does okay. It actually learns pretty quick not to play those, right? Because we get an accurate value and then we'll only ever explore them when we do this exploring. The UCB, of course, does the best because that's like the best algorithm ever. And the FPL, the follow the perturbed leader, does second best. So it's pretty good at narrowing this down. And I used a sigma value of 0.2 here. So pretty large sigma value in the context of 1 to -1. But that seemed to work quite well. Okay, so what have we done? We've learned how to take adaptive exploration by using this FPL, or if you want the Softmax thing, you can now sample according to things and sort of do adaptive exploration as you go, just using the Q values, which might be useful for your projects. All right, any questions or comments about that? Okay, so the next thing we're going to do, and this is what we started the course with, and we're going to end the course with as well, is learn how does this thing work. Where did my paper go? Oh, let me show you a cool picture of a shark that my son was coloring in the other day. That's what we have right now. That will entertain you while I find this this thing. All right. Mastering the game of Go without human knowledge. There we go. All right. Okay. So I'm going to explain how this works. And this is a combination of all the things we've sort of learned so far. So it's based on Monte Carlo learning that you guys did for your assignment. And it's also based on the UCB algorithm. And what we're going to do is we're going to take the UCB algorithm, which involves this like bandit situation with the ends and the trying different things, and we're going to try to figure out how to apply it in a game. So there's a little picture over here with how it works. Yeah, here's the picture that I wanted. So the network starts with a state S1, and then it's doing some thinking, and then it comes out with a distribution pi1. And that thinking, this little picture right here, this little thing over here, oh, I guess I can't circle it. Let me go to the board then. This little arrow, this little down arrow, that is using the UCB algorithm in a smart way. And that is the part, we know the UCB algorithm, and based on that, we're going to figure out this smart arrow. But this is how it thinks for a while about a distribution. It doesn't just like instantly know. It takes the neural network and then uses the neural network to think for a while, and do a search algorithm, and then come up with a distribution pi 1. Then it plays the move according to pi 1, and then it moves to a new state, or it does it again, and again. And at the end of the game, they see the final result they call Z. And then this is the part that should be very familiar to you. This is Monte Carlo learning. So their value of Z gets fed back into the network, and they learn in each of the states, they update their neural network, what they call F theta. They update the neural network to learn the value function V, V1, V2, V3. They update it using Z. That's what these arrows represent. But they also do something else that is new, is they also have their neural network outputs two things, a V and a P. So this is called the policy network. And the policy network directly learns which move to play without having to think of values. And that is sort of new for us. So this is a policy network. Okay, so I'm gonna do, I guess, most of the details next time. Maybe this time, yeah, what I'll do is I'll briefly I'll start describing what these search algorithms are. And then you'll see that the AlphaZero is built on a search algorithm. So this is like the last maybe ingredient we need, are search algorithms. Okay. And so what you should think of for a search algorithm is you should think of a game tree. So let's imagine tic-tac-toe. So one player maybe starts here, and O is deciding what to do. And there are 8 possible moves that O could play for each of the 8 squares. 1, 2, 3, 4, 5, 6, 7, 8. So imagine these are the 8 possible moves. I'll draw out one of them, and then I will get lazy and do a dot, dot, dot. Okay, dot, dot, dot. Okay, maybe I'll do one at the end as well. Okay, so those are the 8 possible moves that you could play. And from each of those 8 moves, there's 7 moves that can come out of those, right? So 7, and so on. And so this is called the game tree. This is called the game tree. And one way to get very good at tic-tac-toe that is completely different than what we've been doing is you can just search through the entire game tree. So what you can do is you can figure out, if I move there, then he could move there, and then I will move there, and then he can move there. And so what you could do is you could go down to the leaves of this game tree. The leaves are, I'm gonna alternate leaves and leaves so that I'll only be half wrong. Okay, leaves of the tree are terminal positions, are end of game, and we can label who won. So at the end of the game, we know exactly what's going on. So imagine, like 8 moves later, it's some filled in tic-tac-toe board with like X, 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 and O. I guess it doesn't have to be 8 moves later. It could be fewer than 8 moves later if you play badly. And then we know for sure this is a win or a loss. I guess we're O, so I'm saying this is a loss. And then if we know the value of all the leaves, we can sort of back up by using game logic, right? If I'm in a situation where any move I play leads to a loss, then that situation is also a loss for me, right? And if I'm in a situation where no matter what my opponent does, I will win, that is a win for me. So I can sort of work my way up the tree, starting with the leaves, and label them, and then go up one level at a time until I figure out that, this move is a win, and maybe, playing on the side, I believe in tic-tac-toe is a loss. So if you play this would be a loss. And so the information kind of flows from the bottom of the tree up to the top. And this is all very nice. This is like a very classical way. This is probably how you think about tic-tac-toe as a human. But unfortunately, it only works for small trees. So the problem with this is, in any realistic game, the size of the tree gets so big so fast that you can't possibly check all the leaves. That's like saying check all the possible ways a chess game can end. Like, it's crazy. You will not be able to do it. So that's why search algorithms, as soon as things get large, they are less effective. So they're very good for small things. One thing you can do is you can try to speed them up by doing smart optimizations. So there's something called alpha beta pruning, here I'll briefly mention, that is commonly used. And it's called pruning. This word pruning comes from the world of gardeners. We're thinking of this as a tree. What would pruning a tree be? You'd like cut off pieces of the tree. And alpha beta pruning, it lets you skip checking certain parts of the tree. Okay, and I'll describe very roughly how it works. So imagine there's a big box over here. Oh, actually, there's two boxes. Okay, so here is the game. You get to choose one box. You choose left box or right box. And then after you choose that, I will choose inside each box. There is another box. So I will either choose, there's two more boxes in each one. There's two more boxes. The up box or the down box or down box. So you get to choose left or right, and then after you choose, I get to choose up or down. This is actually just a game tree with two levels. So this is like left, right is the first level of the game tree, and then up, down is the second level. So this is a very simple game tree with two levels, and I'm going to show you what alpha beta pruning is in this thing. So what I have to do is I have to tell you the values of all these end states. So imagine it's a game with two turns, and at the end, we know the value of the game. So let's say this one, okay, I got to do these correctly. Let me just think for a sec. Yeah, okay, so let's pretend this value is +1, this value is 0, and this value is -5, and let's say this one is +10. Okay. So, and your job is to maximum, you get the dollar amount. You get the dollar amount in the box. Dollar amount in the box. So you're trying to make the money as much as possible. So you're thinking about this, you're like thinking about the states, and by doing thinking, you can figure out what these are because they are the end games of this thing. And so the first thing you analyze is you're like, what is the value of choosing the left box? So I guess I should specify, you get the dollar amount from me. Like I want to make the thing as small as possible. So if you choose the left box, what would happen? Well, I could either choose the up or the down. The up would be $0, and the down would be +$1. Of course, it's my choice of up or down, right? So I get to pick if you get $0 or $1. I would rather you have $0 because I'm the one paying you. So if you choose the left box, then you will get $0. So this 0 value kind of floats up the game tree by 1 and $0. So from your point of view, you have figured out by doing this little thinking and logical exercise that if you choose the left box, you will definitely get $0 because that is the minimum value in the left box, and I am trying to minimize your money. Very nice. Now you start thinking about the right box. And you start thinking about the right box, and you open up the right box. Let's say you open up the down first, and you discover that is a -5. Normally, you could continue. You say like, well, -5, we don't actually know what the value of will be, right? Because like maybe -5 is the best thing. Maybe there's some other really good stuff in there. Maybe there's something even worse than -5. But I claim that you don't even have to think about what else is in there. You never actually have to open this box. So you never have to look into this box. And this idea is alpha beta pruning. The idea that you never have to look in this box is alpha beta pruning. Alpha beta pruning is going to prune. It's like a big scissors that comes and says, hey man, you never have to actually check this thing. Let me draw. This is my cartoon version of scissors. Okay, this turned out way better than I thought it would. Okay, that's amazing. Okay, so the scissors come and they cut off this thing. Why do you never have to check this box? Can anyone think of the logical reason why you would never have to look there? Yeah.
Because the value of whatever you could get there, because the other place trying to minimize.
Yeah.
The better is going to be at most the -5. So
that's right.
Because the other is going to be 0, you don't even have to check.
That's right. So it doesn't matter what's in here. It could be a huge number like +10. It could be a really negative number. Whatever it is, it's not going to change the outcome that choosing the right box can never give me a larger value than the -5. And because choosing the right box is always less than or equal, so basically we know this is less than or equal to -5 here. We don't know its exact value, but it's definitely going to be less than or equal to -5. Could be even worse than -5. But because this is less than or equal to -5, it's never going to be better than the left box, which was 0. So no matter what is here, it's never going to exceed the value that we already are thinking about. And so you can stop checking right there. And so this lets you kind of narrow in on things a lot faster. And for example, Stockfish is based on this. So Stockfish has lots of smart things like this. If you're a chess player, e.g. Stockfish plays chess. And there's all sorts of like other optimizations. When you're doing alpha beta pruning, it's really important you check the best possible moves first. So like if I had done it in the opposite order, if I had opened up the +10 first, then I wouldn't have been able to prune anything, and I would have had to check both boxes. So it's really important you check things in order, and so that's one thing that Stockfish is good at, is like putting the moves in the right order to sort of like explore in the right way. So that is a sort of a classical algorithm, and the algorithm that AlphaGo 0 is based on is also a search algorithm, but it is kind of a more loosey-goosey search algorithm called Monte Carlo tree search. So same kind of idea, and the idea in Monte Carlo tree search is you explore, but randomly. Tree search. So the idea, explore the game tree, but randomly. Randomly. Okay. And why is exploring the game tree randomly helpful? Well, the idea is when you get in these situations, there might be many, many boxes. If you're exploring them randomly, maybe you can get a sense of what's going on by just opening up a few of them, right? You don't need to explore every single thing to figure out what's going on. You can maybe save time by just getting like a representative sample of the things that are happening. So that's the Monte Carlo idea. Okay, and it's based on one thing, one ingredient that we don't have before, which is, I guess, is the Monte Carlo part, which is called random rollouts. Random rollouts. A rollout is you play the game randomly. Play the game. Or at least according to some policy. So a rollout is like expanding the game tree until the end. Play the game until it ends. That's a rollout, and a random rollout is to do it randomly. Okay, so here is what that would look like. Let me start to draw the game tree for tic-tac-toe again. So once again, we have 8 possible options at the beginning. Starting with playing in the top and ending with playing in the bottom. And the idea is to figure out which of these is the best. We're just going to play random games of tic-tac-toe, starting from our 8 possibilities, and we will just see which one of them is the best. So maybe we'll do like 100 simulations from this one. So we'll do like times 100 simulations from this one. We'll do times 100 simulations from this one, times 100 simulations from this one, times 100 simulations from this one. So we'll do 800 games of tic-tac-toe, 100 from each of these positions. And the way people draw these is they draw an arrow like this, and then it ends. So there's 100 things that end in a terminal state. And in a game like tic-tac-toe, 100 is a big number, and you would eventually figure it out. But in a game like chess, playing 100 chess games would barely touch the space of possible things. So we run 100 games with this rollout. For tic-tac-toe, playing purely randomly is a great rollout thing. So it really is a random rollout. And some of these we win, and some of them we lose. We win, some of them we lose. So win. You know, we get some fractions of winning and losings. Win. Maybe this one's, we got really lucky and we won a whole bunch of games. Okay. And then this is the idea. We replace all of this logic of the game tree of like moving back up, like if you play, I play, which is better, all the alpha beta pruning. It just gets replaced with the Monte Carlo thing of, hey, look, we ran 100 games. If I won 66 out of 100 games, then this one gets a score of 66%. This one over here, maybe I won most of my games. Like this one gets a score of 95%, right? And so we're sort of like estimating how good any individual position is by just like how good did it do in the Monte Carlo. And then we're like, oh, what's the best move? Well, it's going to be this one because we won the most games from that position. So that is the essence of Monte Carlo tree search. I guess what I've done so far, there's no real tree. This is just like Monte Carlo search. Monte Carlo tree search is what I described. But in addition, you add in this kind of idea of doing a UCB type thing and exploring a little more carefully. So as you saw over here, I did 100, 100, 100, 100 for each of them. If this was like a chess game, you know, there's a lot of possible moves you could do. Some of the moves are obviously very bad immediately. Like you don't want to like sacrifice your queen for no reason. So instead of checking every single one by 100 times, why don't I check them in order using UCB? So to the actual, what I've described so far is like flat Monte Carlo search. And in actuality, we don't do each of them 100 times. So let me modify by this. We actually do UCB to decide who to think about. So okay, let me Okay, so we use the UCB algorithm to think about, to decide, let's say decide which to simulate. So instead of doing 100 for each of them, maybe we're like, at the beginning, we don't know anything. We haven't tried anybody. So it really is like we're thinking of the situation of having 8 possible moves. We're thinking of that situation like the bandit algorithm with 8 arms. And so at the beginning, we don't know any of them. So we just pick one at random. So maybe we try this one time. We try this one time. And then we do one rollup. So okay, I gotta erase my tentacles over here and draw some new ones. So we do it one time. And let's say it ends with a win. Okay, great. So a win. So our Q value is 1. It's 1 out of 1. Because we've done one simulation and we won one time. Now we decide which one to do next. So we've done one simulation. Which simulation should we do next? Well, this is where it's very important that you initialize your values carefully. If you initialize all these other values to 0, then you would be like, oh, let's do this one. This one's the best one. It's got the best UCB. Let's do it again. And you might get stuck. But hopefully what you've done is you've initialized optimistically, and now your algorithm will choose some other arm. So maybe your algorithm now chooses this arm. And maybe this one is a loss. So we're trying to gain sort of information about the situation by just playing this as if it's a bandit algorithm. So n equals 1, and the Q value is 0 out of 1, because we've done one win and one loss. And you keep going this way, so you choose arms as you go. So maybe sometime later, you've tried this one 10 times, you've tried this one 15 times, this one over here you've tried 20 times. And the more promising ones you try more, you choose according to UCB, say. Choose according to UCB. And the UCB is the average of all the games you've tried, plus, and then you add on some C divided by square root of n, where n is the number of times you've tried each one. And so you want to do that. I guess you have to be careful to not divide by 0. Let's say square root of n plus 1. So you're optimistic. Once you haven't tried a lot, you're trying them more. And so over time, you kind of get back to the picture I had before. But now instead of wasting 100 rounds of thinking about really dumb moves, you spend all of your time doing simulations on good moves. So that is Monte Carlo tree search. Except for there's one extra detail, which is the way I run it, I made it seem like this move is just like a final thing you always run from here. In reality, in Monte Carlo tree search, you build a tree. So real Monte Carlo tree search is exactly what I said, but you build the tree as you go. MCTS is what I said, plus building a tree. Build tree as you go. Okay, so what is it actually? So you start with this position for the third time, and when you think about a move, when we're like, okay, suppose I played this move, suppose I played the first move. The first time we do it, maybe we'll do a simulation. So we'll do one simulation to get 1 out of 1. Ooh, that's a very wide purple thing. Can I undo that? Okay. So, okay, I'm stuck on very wide now. Let's see, can I do? Okay, there we go. So the first time you do it, you do it, and you do 1 out of 1. So when n equals 1, and the average value is 1 out of 1, that's very nice. But the next time we think about it, the next time we want to do computation on this position, we just pretend this position is like the original thing. So the next time we think about it, we're like, okay, let's start making a tree for this position. And this one will have 7 values. And this position has been visited n equals 0 times, and this one has been visited n equals 0 times. So it's like you take the algorithm that we're originally doing for the root node, and you apply that algorithm to this one to decide what to do. And the rule is every time you run a simulation, you add one thing to your tree. So the number of simulations will also be the size of your tree. So after 1 run, we've added 1 thing. After 2 runs, maybe we decide, we're going to try some other move over here. So X, and I don't know, we'll try this one. And then we're like, okay, let's go back to this one. Let's try this now. So we add this to our tree, right? Some other 2 moves deep now. X, O, and then I guess X goes here. I don't know. So as you go, instead of just thinking about 1 level deep, like I originally said, we're going to sort of iteratively apply the algorithm and build this tree that is a mixture of some levels deep and some levels wide, and it's all created automatically by the Monte Carlo idea. So at the end of every single one, we keep track of the number of times we visited each state. So the number here will be 1. This number will get bumped up to 2. And the average will be, say, 1 out of 2 or something, if this one's average is 0 out of 1. So every single node has a number of times we've simulated from it. And so it has some running average of the number of times it won divided by the total number of times we were there. And it has children, and its children are also the same kind of thing. You build it up over time. And then, after you pick some budget of how many simulations you're going to do. And at the end of the budget, you pick whichever is the best at the end of the budget. So you run until out of budget. Run this until simulation budget is exhausted. Okay, so that's the idea behind Monte Carlo tree search. And Monte Carlo tree search, just like regular tree search, it can get really good at games like tic-tac-toe and stuff. But the real $1 million idea is how do we add a neural network to this? Include a neural network. And that's what we're going to see next class. And this is exactly what those Google guys did. So the paper from DeepMind, they figured out a way to incorporate when you are doing the search, so going from the state to this thing, there's a neural network that is helping to guide you. And that neural network is helping to guide you, and it's possible to learn it in a specific way. So we'll see that next class on Thursday. Okay. Also stick around if you have any questions about the homework. It's due on Friday. I think this is the latest day I'm allowed to make it, so that's when it's going to be due. Okay.